can get started. Today we have our pleasure to have Patrick from Virginia Tech. Patrick has been working on neutrino physics for almost 18 years. He's been heavily focused on reactor physics. And today he's going to talk about something that kind of overlaps with politics because you don't get enough of that. Right?
So thanks for the nice introduction. Just made me realize I'm older than I think I am. And so this is not going to be a typical theory talk or anything like that. And the research I'm presenting here is what I call my hobby. Okay, so it's something I do on the side of my regular interest in neutrino physics. But actually, as you're going to see, it has a lot to do with the core things which bother us in neutrino physics. And of course, it has this application to politics. So I never thought I would have a slide like that for a whole number of reasons, okay? And I don't want to get into the sort of tricky one. Let's focus on the upside. So this really ran on Arirang is a Korean TV station. Basically the Voice of America, but the Korean version. So here we go, Trump and Kim shaking hands and all that. So, and that's why the important thing I'm trying to is not this particular one. Nobody knows what's going to happen there, but I will be talking about that one. What is invariably true, since 1945, nuclear weapons and their proliferation, non-proliferation, has been a driving theme of US foreign policy. And that hasn't changed. It doesn't matter whether you have unusual presidents or not. That problem has remained and will remain, okay? And currently we're looking at North Korea to find a solution. A few years ago we were looking at Iran and we really had a solution. And 10 years from now we will be looking at some other country where we try to fix the same problem over and over again. And so the theme of this talk is how maybe neutrinos can help in this conflict. But despite that I do believe that neutrinos can play a role, it's important to keep in mind, and this is also very nicely signified in this picture, it is a political problem. Okay, it's not a technological problem. As long as there's nuclear energy, you have this dual-use nature of this technology, and you have this problem. And the only solution ever will be a political one. But as I'm going to argue that in this early phase where you go from a first handshake to actually having a treaty, and which then can be verified on it, in the first few years of this sort of political normalization, if you like, which eventually does away with nuclear weapons, technical means are important to build trust on both sides, and that's really sort of the phase of neutrinos can hopefully play a role. So now, what makes sense if you talk about these things is to look a little bit on how historically countries got their nuclear weapons. And this is, as far as we know, a complete list. And so it's chronologically ordered. And you see that the US actually started with plutonium from a graphite reactor. This actually is a picture of this reactor. So the fuel would go in here at the front. This is a channel in the reactor. And once it irradiated enough, you push in fresh fuel in the front. The irradiated fuel drops up at the end, and then it goes to reprocessing. The Russians followed the same recipe as the Britons. The French built a reactor which was actually moderated with heavy water. China didn't start out with plutonium, they went the uranium enrichment route. Israel went with plutonium, South Africa went with uranium enrichment, India went with plutonium and heavy water, Pakistan went with uranium enrichment, and North Korea went with this reactor. So basically what you see is you have a 7-to-3 preference for starting with plutonium over uranium enrichment. And one of the reasons plutonium is just ultimately, if you want to have a weapon which you can deliver on top of a missile, you will need a plutonium core. Okay, so to make it light enough. And the three countries which went with uranium enrichment had sort of special situations where this made a lot of sense for them. What's important to keep in mind that these reactors are in the 20 to 200 megawatt range, typically to make plutonium. Okay, that was the wrong button. Let's see. That's and so compared to the reactor I toured this morning, the reactor here from campus is 1 megawatt, so it's way too small to make plutonium. There's a reason that most university research reactors are in a power range where this is a non-concern. That's a problem just solved by the design power. Commercial power reactors which make electricity typically are in the sort of 3 gigawatt range, so they're about 10 times more powerful. And there's a reason why this here is the sweet spot for making plutonium. 20 megawatts makes basically 10 kilograms a year, and that sort of starts to be the lower end of where you have industrial production capability to make bombs, because a bomb requires a few kilograms. And if you make them much larger than 200 megawatts, so for instance, what they do here is called online refueling, which allows you to keep the fuel in the reactor for an exactly prescribed amount of time, which ensures that it has the best quality of plutonium. And having designs like this becomes very hard as the reactors become bigger and more powerful, and so you don't want to make them arbitrarily large. The US has run a few of its plutonium production reactors at 500 megawatts or so in the height of the Cold War, but that's generally was the exception. So it's roughly this range of power the reactors we're looking at. What's important to understand is that a diversion of materials, so the important first thing is to understand that any reactor which uses not highly enriched uranium as fuel will make plutonium as part of its normal operation. And it's not because you're a bad guy, it just happens that the neutrons which strike uranium-238 will eventually make plutonium. And so it's not the question whether somebody is making plutonium, the question is do you know where the plutonium is? Okay, as long as you know where the plutonium is, you are hopefully okay with that. And so you have two things here, the amount of plutonium which is produced and the amount of plutonium which is still in the reactor core. And only if these two numbers diverge, you have a diversion. You have sort of lost plutonium to unknown causes. And so you need to know both of these numbers. And that's really sort of the goal for safeguards. And so now we're sort of going from this more general introduction into the history of nuclear weapons to neutrinos. And so neutrinos in the fission process are not made in the fission process itself, but as a result of the subsequent beta decays. So what's shown here is this cross-section or a snapshot of the chart of isotopes, which is basically the periodic table for nuclear physics. So the neutron number increases in this direction, the proton number increases in this direction, which means everything in the horizontal line are isotopes of the same element. The black boxes are the stable elements. And these colored regions are the distribution of fission fragments you get from various fissile isotopes, and big boxes are U-235, and small boxes are plutonium-239. So first of all, you see you get two distinct peaks. This is at a mass of 140, this is a mass of around 90. You also see they're all produced below the line of stability, which means they have relatively too many neutrons to be stable. These neutrons will undergo beta decay, and you proceed this beta decay along these diagonals until you eventually hit the stable element, and then it stops. Okay? And so it's these beta decays to stability which give you your neutrinos. And if the only task was to predict how many neutrinos are produced, it's very easy because you have baryon number conservation, right? You're not losing neutrons and all that. It's a very simple calculation. We can calculate that number very precisely. But since the interaction rate of neutrinos is proportional to the energy squared, I need to also predict the energy spectrum. That's the hard part, and once you did that. And what you also can see is that uranium and plutonium have different distributions. Here in the high mass peak, you can't really distinguish the colors, they're very similar. But in the low mass peak, you see that plutonium is shifted upwards. Can even tell you how much it shifted upwards? Exactly shifted up to 4 units. They start with 4 more nucleons, and they're not losing nucleons in the process. They have to be somewhere, so they will be the fission fragments. And so that's why, so this is, the mean value is shifted by exactly 4 nucleons, which also indicates that the plutonium beta decays are different than the uranium beta decays. And so we can expect that the neutrino spectrum coming from plutonium fission is different from uranium fission. And that's one of the core observations which allows neutrino reactor monitoring. As I said, we can compute the number of neutrinos quite nicely. If you do this sort of simple calculation, you find about that we need 6 antineutrinos. We can do this more precisely, as I said, but it doesn't matter because we're really only interested in the ones above the speed decay threshold, and that computation requires the energies, which is very hard, and I'm not going to drag you through that. That's a different talk, and it's very interesting too, but it's not the subject of today's presentation. So now we can compute the spectrum we're getting from the 4 different isotopes, which these 4 fissile isotopes make up 99.9% efficiency in the reactor, which is based on the uranium fuel cycle. So you start with U-235. As you progress in the reactor cycle, you make plutonium-239 and 241. You always have uranium-238 in these reactors. Uranium-238 undergoes only fast neutron fission, which in this figure here would mean there are a lot of fission fragments in this intermediate region. So the spectrum from U-238 is very different. And as you can see, if I plot this at equal power, equal number of fissions, if you would like, you see 238 makes the most neutrinos. And this, by the way, has been followed with stable better decay cross section. So this really would be event rates, followed by 235, followed by 241, followed by 239. Now, if you equalize them, normalize them to the area, then you can see that uranium-238 has the hardest spectrum, plutonium-239 is the softest spectrum. So from that, you can predict what happens if you run a reactor. You start with mostly U-235, which has a harder spectrum at a higher rate, and then you go to more plutonium, which has a softer spectrum and a lower rate. Okay, you see both the spectrum becoming soft and the rate becoming lower as you go through the reactor cycle. And of course, this has been observed. Reactor monitoring has been proposed by Lev Mikelian in the 70s, and he was working at the Kurchatov Institute, and they also then went and did some experimental studies. So this here is reactor power in megawatts. This here is your neutrino count rate per day, and you don't need a fancy analysis to see that these two things are highly correlated. Okay. But also what they see here, they take the ratio of the reactor spectrum at the end and the beginning, subtract that from 1, and you see the spectrum becomes softer. So the dashed line is their prediction. Becomes softer as the reactor cycle progresses. The error bars are very large, but this is also all not very new stuff. This is 20, 30 years old.
And the softening is important for power reactors, but not for
no, it actually will come there. And then this was a power reactor. For what follows, I will introduce what I call the standard detector, which actually is supposed to fit inside the shipping container. So this has that many target protons. In pure scintillator, it's about 5 to 8 tons of scintillator. A container like this can hold about 20 tons, so you can fit this in there very easily. The assumption is that you have no overburden, so you really operate this in a parking lot, and so therefore we'll have a irreducible cosmogenic background. And you have to understand, when we started to do the studies, this was a highly hypothetical object. Okay? And that the whole sort of message of this talk is we've gotten from this being sort of a spherical chaos theorist detector to real existing detectors which are very close to me now. So that really has changed over the last 10 years, if you would like. All right, so to show you how the energy spectrum can be exploited, to come back to your question. So this here shows the event rate spectrum in this hypothetical detector at 20 meters from the reactor. And so you see here at 45 days in the reactor, you get these black dots. And at 350 days in the reactor cycle, you get the blue histogram. It's easier to subtract them. So you see that you have more high energy events early on and fewer, more low energy events in the late spectrum, and fewer high energy events in the early spectrum, and fewer high energy events, you get the shift. This reactor core, at this point, the difference is about 7 kilograms of plutonium, which as I've told you previously, you can figure out that the thermal power of this reactor is in the 20 to 50 megawatt range. In this particular case, it's a 40 megawatt range. And so the trick is, if you can measure this here reliably, then we can measure the plutonium content of the reactor. Okay. And then you can look at different reactor types. And so what you do here, basically based on this type of spectra, you can do random chi-square analysis and all that sort of stuff, and try to fold in some error systematics. And then here you can show, this is your ability to measure the plutonium content in kilograms. This is the thermal power of the reactor. And you see that actually it generally becomes harder to measure plutonium as the reactor becomes larger. That seems to be counterintuitive, but you have to understand, as the reactor becomes larger, my event rate goes up, but my error bars only go up like this, or my relative errors only improve like the square root of that. But the total plutonium content also scales with the thermal power, so I actually start to lose. So this is a curve as a slope of 1/2. And so you see some reactors are easy, so this are here, this would be a reactor running on highly enriched uranium. This would be a reactor, this is characteristic of a typical power reactor. This is the graphite reactors, which tend to be hard. And the goal would be to, at one signal, detect 4 or 5 kilograms within 90 days. And you see for many reactors you can achieve this over a wide range of reactor powers. All right. What was also important to realize is reactor physics makes fission fractions in each isotopes, they're not free independent parameters. It's very simple. If my reactor makes 1 megawatt, and half a megawatt comes from uranium, the other half megawatt has to come from plutonium. Okay, that's essentially what he's saying, is that there's a unitarity bound, and they correlate. And since it's only 4 isotopes, this is an important bond, and so that's really why this is useful. So you see, for instance, here how the fission fractions here evolve as time in the reactor. The unit people like to use is megawatt days per ton. This is really megawatt days, this is units of joules, right? This is energy. So this is the energy extracted per ton of material. If you know how large the reactor core is, then this becomes a time axis at full reactor power. And so you see U-238 stays flat, plutonium-239 is produced, 235 decreases, and if you do this here is based on a real reactor simulation. And if you just plot the correlation of the two, you see very clearly that it's on a perfectly straight line. Any power not produced by uranium has to be produced by plutonium. And the reactor power is kept constant not by physics, but by the operator. That's what they do with the control rods and all that. Despite the fact that the core changes, they keep the power constant. All right. So let's go to one sort of the early examples where just to give you a flavor of how these things unfold. Is actually North Korea has been a problem much earlier than today. So there was a crisis in the mid-90s. That was before they had nuclear weapons. So finally North Korea, after long negotiations, decided to basically sign the Treaty for the Non-Proliferation of Nuclear Weapons. And so inspections in earnest started in 1992. So the IAEA is the International Atomic Energy Agency. And how this works is, so you basically, when you start becoming a member of this NPT club, you basically make an initial declaration to the IAEA and say, okay, this is the stuff we have. And then the IAEA comes in and tries with inspections to verify that. So the North Koreans stated that they have 60 grams of plutonium or so, which is separated from a small batch of fuel. And so what then happens, the IAEA came in and took samples at various stages of their waste stream. And so you need to pay attention to the fraction of plutonium-240, and you see that these here, the first three are about the same as 2.2%. But you see the latter two are 1.3 and 1.6%. Now the ratio of plutonium-239 to 240 in the waste stream or in the fuel depends on how long the stuff was in the reactor core. Okay? This was fuel which was long in the reactor core, you have a lot of 240. This was fuel which was not so long in the reactor core because you have little 240. And so just from these isotopic ratios, the IAEA knew this was not a single batch of fuel which had been reprocessed, so they reprocessed fuel of different ages, and so probably therefore they reprocessed more than one batch of fuel, probably 60-gram declaration is wrong. Of course now we know, yeah, that was BS, they had about 8 or 9 kilograms at that time. But we didn't know this back then. And interesting enough, I should say, is a lot of this information was gleaned not from taking a bucket full of relative waste, but by doing swipe samples. So basically you take a material which looks very much like a coffee filter. You swipe this over the surface, you put this in a little baggie, you send it off to your low background counting lab. And basically micrograms of dust collected are enough to allow you to do this analysis. And the North Koreans didn't anticipate that the IAEA had the technical capability to do this. Otherwise they would have cleaned the rooms much better. And then the whole story was what to do next. And so the real question here is, so now so this now is the running history of the North Korean reactor, which used to make this plutonium. This reactor started in the mid-80s. And so basically the story the North Koreans told the IAEA is that the reactor was running at various power levels, and this specific plot, the slope here is the power of the reactor. So if there's no slope, the reactor is off. And it's this period which was known from satellite observations that the reactor was shut down for some 50 days or so. And the question was, did they take out all the fuel at that point and reprocess the whole batch, at which point they would have 8 or 9 kilograms of plutonium? Or did they, as the North Koreans said, take out just a few fuel rods and process to 60 grams? And the difference would be that if you put in a fresh core, then that starts at 0 burn up and evolves with time. And the trick is now, if in this period of time the power was as low as the North Koreans say, then the old core gets into this burn-up or age of the reactor, if you would like. If you burn at much higher slope, that is at much higher power, you can get the new core to the same burn-up. And of course, they quoted this power history knowing full well that those two would match. You realize access of the IAEA was at this point in time. So this shows that, by the way, that these people know nuclear physics as well as we do. After all, they're able to build nuclear bombs, so they understand something. So that's, by the way, a big theme recurring in these things. They always assume that the other people are more stupid than we are, and that's not a good assumption. I know, especially as theoretical physicists, this is built into our system, okay? But it's not true. Then you can do, based on this data, a very detailed reactor simulation. I'm not going to bore you with that. And then they can show you what you would have seen in neutrinos had you had neutrinos. And here now we measure directly the number of fissions in plutonium as a function of time. And you see this is the blue lines is the story the North Koreans gave, and the orange line is what probably really happened. And you clearly see that in this period where the reactor is running at different power, I'm not only seeing a different slope, but I really see very different plutonium fission fractions. And so that would have been an indication that something goes wrong. Of course, this is counterfactual. During that time, we did not have access to the reactor. And if we had access to the reactor, the North Koreans would have fabricated a different story. And that's clear. Then this is sort of a map of the lay of the land there. This is a big sort of map of Yongbyon. So here's this 5 megawatt electric reactor, which really is a 20 megawatt thermal reactor. And here's an old research reactor they have been operating since the 70s or so, which was a gift from Russia. This is a reactor which is not so different from the one we have here on campus. This here has maybe 2 or 3 megawatts of electric power. And so the story we're trying to tell here is if I had this reactor was under IAEA safeguards since the 70s. So if the IAEA had a neutrino detector there since the 70s, that neutrino detector also could have seen signs of this reactor operation. After all, they're only 1.2 kilometers away. Okay? And that would have given signs that this reactor is used in a different way than suspected. And the other things we're going to talk more about is that not only reactors make neutrinos, but the radioactive waste from a reactor contains mostly strontium-90, which is a 28-year half-life, and we can detect neutrinos from that in principle.
So we say, where's the detector here?
The detectors would be here, these little crosses, right at the reactors. And here, this would be the sites where we would be looking for.
But this is the North Korean Korea.
This is North Korea. The assumption is what would have happened if we had this.
Oh, okay. So we're not putting this like into demilitarized zone, right?
That's a different story. We'll talk about that. But we come back to it. All right, so I'm not going to drag you through that. That's very burdensome. Okay, let's fast forward the next nuclear crisis some 20 years later. So this was Iran in 2040. So this is the reactor I've shown you in the beginning with the 7 kilograms of plutonium. This is the 40 megawatt heavy water moderate naturally uranium-fueled reactor, which never went into operation, but in 2014 this wasn't clear, right? Remember, that's the time when the Iran deal was negotiated. This thing, if it were running, would produce about 10 kilograms of weapons-using plutonium a year. That's one of the reasons this was a major concern in these treaty negotiations. So what could we do for this reactor? And so for this reactor, I'd like to sort of introduce this fictional scenario. So what I call the nth month scenario. So you have full inspector access for n-1 month, so everything is working as it should. The reactor shuts down in the nth months. And then you have what's called, in safeguard speak, a loss of the continuity of knowledge in the nth months. And so basically what we mean by that is that you lose access to the reactor for whatever reasons. This could be a technical glitch. Your camera runs out of battery. This is hacked. IAEA is operating thousands of cameras around the world. Once in a while they fail. Okay? And it takes you often days or weeks to get an inspector there to change the battery. Right? You could have diplomatic tensions. Somebody could send an inappropriate tweet or something like that, and in reaction to that, your hosts tell you, go get lost, we no longer like you. Or, of course, you could be in the case where there is indeed malfeasance and they try to break up of the treaty into a diversion. Of course, distinguishing these cases is really important because determines very much what the steps follow next. And so this is how this would look like. So here you have now the reactor core content with plutonium in kilograms, and here the time the reactor has been running. So in blue, this is sort of your n-1 month, and you can measure the plutonium content roughly with this error bar. Then you have this nth month scenario, the reactor is shut down, but you have no access to the reactor core during that time. And once you get access back, you're presented with a running reactor, the reactor core is shut, so you cannot access the reactor core directly. And so if nothing has happened, then you would be on this blue line, so it's the same core. And if they replace the core with a fresh one, so now they have the core in hand outside of the reactor, which is 10 kilograms of plutonium, then you get this sort of difference, and it's about a 5 sigma difference, or in 1 sigma errors is 1.2 kilograms of plutonium. I should point out this, in safeguards, nobody's interested in 5 sigma statements. It's all 90-95% confidence in things that work. Okay? That means it takes you about 7 days to declare an undeclared, to detect an undeclared refueling at 90% confidence. All right. Of course, so that treaty has been shot to pieces, but still, the analog here with plutonium measurements is the following one. So so we all have cars. So the speed in the car will correspond to the thermal power of a reactor. The trip mileage is actually a burn-up. The used gas is the produced plutonium. And there are, of course, 2 ways of how you can reckon how much fuel you have in the gas. You can use this number here, knowing your gas mileage. You can compute how much gas you have used and how much should be left in the car. And if you're a good physics grad, then you may have driven at one point in your life a car which is old enough that was the only way which really worked. You also know this is not terribly reliable, and if you're suspecting, for instance, your neighbor siphoning your gas tank, then this is not a great way of knowing what's going on, because the only time you will know this is when you go back to the gas station and refuel. Same as a reactor. Okay, only when you refuel you know something was wrong. And if somebody basically doesn't allow you to see how much gas you put in because somebody else refuels your car for you, you have no information how much gas you really used. Isn't it nice that most cars for that reason are equipped with one of these, a fuel gauge? You just look at the darn thing, you know how much fuel you have. And that's really what neutrinos give you. They directly measure the amount of plutonium in the reactor core without having to do any crazy bookkeeping or keeping records and stuff like that. And I think that's the reason why cars is generally accepted having one of these is a really useful thing. All right. Good. The next big thing here is in this business, of course, this is of particular local interest, is coherent elastic Neutrino spectrum. We've seen about 5 million invertibility K-events from reactors, but this reaction is a threshold of 1.8 MeV, and of course the detectors are in the ton scale range. The 7s we can go below the IBD threshold, but just to make this clear, the recoil energies for 1.8 MeV neutrino, these are the maximum recoil energies, are small for any conceivable reactor material, detector material. And if you account for quenching all these things, this would really correspond to very low detector thresholds we need to reach. So it's not clear you can do this. And as a result, very little work has been done for the reactor fluxes at below 1.8 MeV. And so we're really not quite sure what we're going to find there. One thing which is important is that we have these breeding reactions. So this is how actually uranium-238 becomes plutonium. So you capture a neutron, which gives you uranium-239, which better decays in about a day, to neptunium-239, which better decays in another day or so, to plutonium-239. These two better decays have antineutrinos, but they have antineutrinos only 1.5 MeV or so, which is below IBD threshold. They cannot see them. But this neutrino flux exceeds the neutrino flux from anything else at that energy. Okay, that's the biggest flux from a reactor below 2 MeV comes from these neutrinos. So if you could see them, you would have a direct measure of this breeding reaction. That would be very attractive. The other thing is that you have these structural materials in reactor cores, which actually also can do neutron capture, then produce neutrinos. And this is actually not such a low energy neutrino, but we have neglected it because it really, a power reactor has no aluminum in the core, different for small reactors. Nuclear engineers like aluminum a lot because it's a single isotope. It really has this pure isotopic composition, is no long lived activation products. So it's a nice structural material in reactors. And so that can become an interesting problem if you try to explore this more precisely. So to show you why this breeding neutrino thing is interesting. So, interesting enough, the world overall has way too much plutonium. So as a fact, there has been a treaty between the US and Russia, which of course also has been chopped to pieces, but in principle in this treaty, both sides agreed to get rid of 20 tons of weapons worth of plutonium they no longer need. So how do you get rid of plutonium? You just cannot, bury it in your backyard and hope it's going to be fine. So one way was to burn it in a nuclear reactor. Makes sense, extract energy from the thing and at the same time destroy it. And one proposal was to use fast breeder reactors, because actually plutonium is a little bit tricky in a regular reactor. And, remember the MOX plant disaster. So there are some reasons why running as a normal reactor is tricky, so you can run this in a fast breeder reactor. So this is sort of a wedge, so you have to imagine 6 copies, then you get a full reactor core. And you see you have your several zones in the reactor. What is interesting is here that you can have this external blanket, which if you fill this with natural uranium, then you can burn plutonium here, but make new plutonium there. As a matter of fact, you can make more plutonium here than you burn in the middle. Actually, especially also you could make much better plutonium than the one you burn in the middle. So for this thing to really destroy plutonium, you need to verify that there's no breeding blanket. The problem is, in a normal reactor core, I open the lid and look in the core, which I can because the coolant is water and water is transparent. Fast breeder reactors, the coolant is liquid sodium, which ain't transparent. So even if I open up the thing, I cannot see what's inside. Okay, and so therefore verifying the presence of a blanket is tricky. So now, and of course, when the reactor is running, this part here is fissioning like crazy at, I don't know, 1,000 megawatts or so. There are very few fissions in this blanket, so radiation signatures from the blanket are nearly invisible because they're blinded by the reactor. So now with 7s, I have access to these low energy breeding neutrinos. And with breeding neutrinos, the blanket is as bright as the core because there's a lot of breeding going on. So in principle, I should be able to see it. And so this here is the simulated event break you get as a function of recoil energy in a silicon detector. And you see that in the absence of a breeding blanket, I get this spectrum, and in the presence of a breeding blanket, I get this spectrum. And of course, they're reasonably far apart, and I can tell them apart. It's 10 kilograms, so this is not just one of the Coney CCDs, but a really big bag full. Then, of course, there's no quenching applied to this, which probably means that things go down. And of course, you realize if your quenching calculation is slightly wrong, then the 2 curves become completely identical. So this is, again, the theory of approximation to the whole thing. But it shows you that in principle, this detector sizes which are not arbitrary and feasible, you may have access to this.
What threshold do you have?
Pardon?
What threshold is it?
Oh no, you draw your threshold as a line in here and tell me what's left. Okay. And the answer is your threshold better be low if you want to do this.
The differences will much less.
Right, and if your threshold is 100, then I think the 2 curves, once you account for any sort of realistic systematics, are undistinguishable. If your threshold is 50, maybe in business, and if your threshold is, I don't know, 20, then it becomes probably reasonable. That's really the message. And you need to really understand the low energy. It's not only the threshold, you need to understand the low energy response of your detector extremely well to pull this off. So this is in reality a challenging measurement. But I'm a theorist, I don't have to build it. So. Okay. So now we come to this sort of part which is all fine and theoretic, to where we sort of reasonably make progress. And so, what happened over the past 10 years, but in reality, really over the last 3 years, is that we have seen enormous progress in building neutrino detectors for reactor neutrinos, which use inner-speed decay, which can do this at the surface. So this is not because people want to deploy reactor detectors in North Korea. This is because people want to get a ticket to Stockholm for discovering stellar neutrinos. And that seems to be a better motivation for physicists than pretty much anything else. And in the last 3 years, you've seen an explosion of experiments doing this. I mean, there are dozens of collaborations out there who tried to put a small detector at reactors not so dissimilar from the one you have here. And what happened this year is the Prospect really announced a very nice result. So this year is they can't break a reactor on, reactor off, and this shows you also as a function of distance, this follows a 1/r scale. What's remarkable about Prospect is that it's doing this at the surface. So you remember I've shown you this data from the Kachatov Institute in the 80s and 90s. They could do this because they had a unique reactor at Rotherham which was underground. So they could deploy the detectors deep underground, and we can detect reactor neutrinos with enough overburden since the dark days of Cohn and Reines. okay? What's really new with Prospect is they can do this without having a mountain on top of them. And that's, of course, the key ingredient to make this blue box detector work is I need to get rid of the mountain on top of it. Fitting a regular neutrino detector in a shipping container is never was the problem. The problem was that you need overburden. Prospect has done away with that, and they can reach a signal to noise of roughly 1 to 1, okay, at the surface. And that's really that's very useful. So what this is how it's going to be the scaling relationships they're going to be using for the next thing. That's the signal they have seen. This is the background they have seen, and this is the reactor power they had. That's the distance, that's the detector mass. And the scaling from there on is fairly trivial. This you can do in an algebra-based physics, so no calculus required. Okay, so the first question you can ask about, so what we're doing now is we take this measured performance of Prospect and apply them to the various use cases or scenarios for using these detectors and say, how well do we do with that thing? So the simplest thing to ask is the reactor on or off. Okay, the simplest thing to ask is really, is there a reactor? But the next thing you can ask is on or off. And so here we use time to 95% confidence level detection based on the Prospect size detector with Prospect backgrounds. So basically I'm saying is take Prospect as it stands at HEPEC, put it to your favorite reactor and ask the question, can we do this? So the 3 reactors I'm looking at in detail are the 5 megawatt reactor. Sorry, I probably should go back. I should get I'm not going to get there. But there was a slide which had that information, so let me provide it now. This is a 20 megawatt graphite moderated reactor. This is a 40 megawatt heavy moderated reactor. And this is the experimental light water reactor, which may be in the process of being turned on in North Korea, which is a 100 megawatt light water moderated reactor. And you see at the 5 megawatt it takes us 2 days. At the IR40 it takes 12 hours, and the bigger reactor it takes 2 hours. So if you want to know whether this thing is on or off, Prospect like Detector can do this very nicely. Okay, so it's not a problem. Just to point out where 7 stands, so if you just take the CONUS presentation at Neutrino 2018, so CONUS is germanium detectors at close to the reactor core in Germany. They didn't report really detection, but if you just scale their signal numbers and background numbers, you see that they basically need a 7.5 ton years of exposure to do this at the 5 megawatt reactor, because their signal to noise is like 1 in 100. Okay, and so that means it's extremely hard for them to ever see that. And it shows you that while the detectors may be only this big, you're not getting a huge capability out of them at this stage. I'm not saying this is the permanent status of the thing. It's not the signal is tiny. The problem is the backgrounds are enormous because a nuclear recoil has no signature. And you're living in an environment where you're seeing neutrons from the reactor. CONUS certainly does. Okay. All right. Then the other thing you can look at, and so now this is another map of Yongbyon, and now we can talk more about what we see here. So this is the 5 megawatt reactor. This is this experimental light water reactor. You see the building is ready, and their indication there was a article in the New York Times earlier this year reporting a lot of activity around this thing, so they may be in the process of turning this on. Here you also see the fence around the facility highlighted. This is the river they use for cooling water. And so the idea would be that you deploy here a detector, so you basically take Prospect, stick it in a shipping container, and then you surround this with some shipping containers filled with a little bit of water to give you a little bit of shielding. And you can all transport this by truck, so that's not doable. And so these circles here indicate 50 meters around the reactor, which is sort of the location you'd like to be. So what we're looking here, however, is the midfield. So what if you have to stay outside this fence? This could be very conceivably a negotiation to solve that the North Koreans say, okay, neutrinos are great, but you're not getting inside the fences, these things. Then you have to revert to detectors which are diabase-like, larger detectors than Prospect can be used, a single volume detector, but now you need overburden. As it happens, there's a mountain here, roughly here's the peak called Yangsan, and this contours, elevation contours, and you see that here's 60 meters. So if you drill horizontally, then you reach 160 meters, 100 meters of rock overburden at a distance of about 800 meters from the reactor core. So if you stick a diabase-like detector under this mountain here, that's roughly the overburden diabase has. And you use diabase backgrounds now. Then it takes about 100 days to detect this thing being on, and it takes about a week to know that this thing is on. Now 100 days seems a long time, but you have to remind yourself that this reactor requires 450 days or 500 days to make 8 kilograms of plutonium. So you still would know early on before they have made any relevant quantities of plutonium whether this reactor is okay. All right. Then the next thing beyond reactor on or off, you can ask yourself, would we detect this core swap scenario? We have we're worried about in the 90s. And so what's important here are, again, the days, the detection of 95% confidence level. And let's assume we have the current background levels as a prospect. You see, for the ELWR and the IR40, they can do this well below the time they need to make 8 kilograms of plutonium. It's about half the time. You see, for the 5 megawatt, I cannot. This takes a long, long time. You see, even in the case of no backgrounds, it still is barely feasible. But you see, if I reduce the backgrounds by only a factor of 2, the times really start to shrink considerably and become much more attractive. And so you see that for reactors, which are not this one, this is something you probably can do nowadays. For the 5 megawatt reactor, it remains very difficult. That has to do with
What's your background level? What's the unit? Is that area?
One is, I scale the prospect background.
Prospect.
So prospect is 1. And I'm just using that because I don't have to make any silly theoretic arguments of backgrounds. Just go to the paper and say that's what they've reported. And I'm not saying that that's the ultimate performance these detectors can have. It's just an existing. And I think that's where the difference is, that now we have existing detectors which can do this. All right, then let's go to this spent fuel detection scenario. So this here is a Neutrino Spectrum from a reactor as a function of time after shutdown. So at 1 minute you have this spectrum. At 1 hour you have this spectrum. And you really see certain isotopes dying away. Okay? Then krypton dies away, then ruthenium dies away. And you see the thing which is left at the end at 10 years and 100 years is strontium. Okay? And so the question, and so this is the most beautiful threshold. So you see there's not a lot above that, but can we see this principle? What's interesting is that this strontium stays in the reprocessing waste. So if you extract the plutonium off your fuel, the strontium goes into the waste. And so now, if your interest is not maybe necessarily to verify a shutdown, but historically find out how much plutonium did they ever make after they declared all the plutonium to us, then if you could account for all the strontium, you have a very nice way of knowing how much plutonium was made, because there's a one-to-one correspondence. The problem is, of course, the rates are low, right? I mean, this is a log scale, is 7 orders of magnitude. And so we're not using the full 7 orders of magnitude, but this is still 3 or 4 orders of magnitude flux difference. So that ain't helping. And it's all very low energy, which makes neutrino detection generally harder because the background's become more. So let's go back to this Korean example. If you make 8 kilograms of plutonium, you make about 2 moles worth of strontium-90. This here is, by the way, the North Korean processing plant. So you see this long building. That's basically a deep trench in the ground of hot cells, right, which are accessed from the top. You put in stuff from the top, you work from the sides. This is like, looks like Hanford, not accidentally. And 2 moles of strontium-90 give you about 55 IBD events in this blue box detected at 10 meters in 1 year. Okay, that's not a huge rate, but rates which have been detected in other experiments. Okay, and then you can do the exercise and you take existing backgrounds from prospect. Okay, finding 8 kilograms of one significant quantity takes you 270 years, probably not going to happen. And even if you reduce your backgrounds to a 10th, it's still very hard. You need to basically have a background-free detector if you want to take one significant quantity. But of course, the point is the Koreans have a program which has between 10 and 100 significant quantities separated. And here you see things perk up because the signal really goes up. And even with the background of 1, as prospect has, it takes about 2.7 years to find that stuff. And so even if this is buried on the ground, you have a chance to actually do this sometimes because where this matters. But clearly, the lower the backgrounds become, the better your situation is to actually do this. And of course, here at 10 meters, you really would like to extend this to a range of 50 to 100 meters where you can do sort of site-wide search, and then really have to get down the backgrounds. All right. So this, I have to say this because actually it was part of that. So this is the mobile neutrino lab. So the trailer, which contains this thing, which we call a fractional chandler. So this really fits on a table. So this is on each side about half a meter. And so we took this to the North End nuclear power plant, and this is the signal we're seeing. So it's about 5 sigmas for IBD. So if we had managed to do this in 1951, that would have been the Nobel Prize. Doing this in 2018 just means, oh great, you could do this as well. But of course the trick is that this thing has no overburden. The overburden is really the aluminum roof and the air conditioners. And so it shows you that this can be done in very small detectors. There are other efforts going on at Virginia Tech based on segmented detectors. And so these detectors were, the initial goal was to develop detectors with Untitled detection, but of course they're very well suited for these applications. So that already brings me sort of to the summary here. So Antineutrino monitoring does provide good security-related sensitivities for a wide range of small to medium-sized reactors. And for near field, so that's everything maybe up to 100 meters from the reactor core, detector capability is existing. Prospect shows that we can do this. The trick is now to take Prospect, put it in a can, and ship it to the other side of the world, and have it run there. 3D segmented detectors, right? Prospect is 2D segmented. 3D segmented detectors combined with pulse shift discrimination probably can push backwards another quarter of magnitude. Questions, can we ever do this without any liquids? We don't know. And liquids, so you have to understand that scintillators have undergone an evolution. The first scintillators used to be shear, so were highly flammable things, were very toxic, basically were like gasoline. Modern scintillators like LAB or so are, used in soap. They're less flammable than diesel fuel, for instance. They're not toxic, but they're still liquids. And the point is, if your host nation wants to be not nice to you, they say, okay, Neutrino is not a problem, but you're not bringing any liquids, right? So then you have a real problem. So it would be nice to have solid plastic. Also, liquids have an aging problem, which plastic doesn't have. I think what's still missing is a calibration of Antineutrino yields. We have seen first studies of reactive, how the Neutrino spectrum changes throughout the reactor fuel evolution. IFA has published a paper and so on. But the error bars on that are still large, and it's only for a very limited number of reactor types, so that needs to become better if you really want to use this in the field. I think the seventh with reactors, first of all, needs yet to be demonstrated. And I just want to be clear, in IVD, between the first demonstration and the first point in time where we can maybe do this for real, it took us 7 years. Okay, so 7 is maybe much faster, but between the first demonstration and having the field deployable technology, that takes a while. I think we're very close to this demonstration, and you're working hard on that. On the other groups which try to do so, I think within the next 12 months, somebody will raise their hand and say, yes, we have seen this. But to explore these capabilities, they have low enough thresholds to go below the IVD threshold and so on and so forth. That still will remain a challenge. And it's a very different thing saying, I've seen a 2 sigma or a 5 sigma signal from a 3 gigawatt reactor, whereas to say, to be able to go to a smaller reactor where maybe not 5 meters from the core, but 25 meters from the core. But it's getting there, and I think it's going to be interesting. It is an interesting emerging capability. Of course, the basic science reach of these things is going to be really exciting, irrespective of what safeguards. For safeguards, I think what's important is that you can use Neutrinos to detect the core swap within a few months, even with demonstrated background levels. And this core swap scenario may seem very artificial, but essentially it's exactly the situation you had in North Korea in the mid-90s. It was a concern for the Iranian case, which led to the reactor not being part of the deal, right? They shut it down as part of it. It's fair to say, if you look at the Korean deal, first of all, if there is a new deal with Korea, who knows? This experimental light water reactor is something the Koreans most likely will not be willing to give up because they see this as a way to energy independence. As you know, or may not know, but North Korea is extremely dependent on energy imports, which basically all come via China right now. And they would like to be less dependent on these. They actually have a reasonable amount of uranium in the country, a lot more than you would expect. Actually, probably a lot of the early Soviet uranium for their weapons program came from North Korea. So they have actually pretty good uranium supplies. So it is an argument which is not totally unreasonable, and certainly for the North Korean leadership an important one. So if you have to run this reactor, you will need very robust safeguards which can actually survive a treating president and 2 hot heads on both sides of this thing. And Neutrinos can provide this capability. The other thing is Antineutrino monitoring is non-intrusive. Okay? All other means to monitor a reactor involved inside the reactor building, that you have cameras, seals, that you're present during refueling, that you generate a oil paint in the behind of whoever's running the reactor. That's, by the way, even true. This is a problem not encountered in this country, but if you talk to reactor operators in Germany, they will admit that having the IEA there during refueling is not particularly something they enjoy, because during refueling, a reactor has about 5 times as much staff as it has under regular operating conditions. It's already like your madhouse. This is basically having your in-laws visit you while you're moving apartments, okay? And so it's much less intrusive if all you do is park a blue box outside the building and otherwise stay out of everybody's way. And it can be done at a running reactor in situ, so it's not like you have to wait for this prescribed moments in time when the reactor is shut down to learn what's the state of the reactor core, which can be postponed into the indefinite future in principle. This is sort of quasi real time. This is probably not so relevant for this audience. So the IAEA, so the one question you get in this context is, oh, what does the International Atomic Energy Agency say about neutrinos? And they say, oh, and the answer is basically, oh, this is very interesting. Come back if you have a neutrino detector this size for $5,000. That's paraphrasing, but not far away from the attitude. So you have to understand that IE safeguards are implemented according to these documents. So this is the regular safeguards agreement and this additional protocol, they're each about 20 pages. They're not so complicated, but basically they're all based on a mutual assumption of trust and the fact that the IAEA has to manage 450 reactors with a budget of $130 million a year. Okay, you clearly can see that neutrino detectors are not within the budget of the IAEA. Even a cheap neutrino detector is a couple of million. Okay, it's not going to happen. And reactors are not the main concern in this context. Regional nuclear deals, I think, offer a much better case. So the case, for instance, with the Iran deal is the safeguards in Iran cost about $25 million a year as per this deal. This is not coming out of IAEA's regular budget. This is coming from extra money funneled to the IAEA from the US and Germany and other countries to make sure that this deal can happen. And the same, so that would eliminate this whole price point problem. If you have a deal with Korea, somebody will happily pay another $10 million for a neutrino detector if this makes the deal more acceptable on both sides. And so I think this is really going to be one of the first demonstration cases. Is a situation like North Korea. So I'm not saying that North Korea will have a neutrino detector, but as I said in the introduction, I'm convinced they will be the next North Korea in the sense that this nuclear problem is not going to go away. And so that's that. Thanks.
Are there any questions?
Yeah, so the aluminum being the source
Yeah.
of neutrino, that's something I learned this month in the talk. So that's really interesting. You're saying that can be comparable in flux to the actual reactor core.
That's what the authors of that paper claim.
Yes. So I mean, in principle, like we could negotiate with the reactor guys, put more aluminum, for example.
So this actually raises an interesting question. Can we find this here? It was not very far back. So, Michelium proposed to have custom-made, reactor core contents. So, for instance, if you put lithium in there, you get isotope, right? Lithium-7 captures, makes lithium-8, gives you a very high energy neutrino flux.
Right.
So yes, you could make custom reactor cores which have custom fluxes. That's a serious possibility, and I think at HIFA they would tell you to go away because they have a very specially designed reactor core. But if you happen to have a cooperative small reactor, like I've heard you have a good relation with your reactor operator, there's maybe nothing wrong in adding lithium-7 to that reactor and make a high energy 12 MeV neutrino flux.
Yeah. I mean, even the 2 MeV, 2.8 MeV, that's really.
I'm just saying, if for instance, if you wanted to prove that your coherent scattering signal is coherent scattering, the neutral fluxes don't change.
Right.
If you fiddle with that and show it changes in an expected way, you have a way to do
It's
this.
an independent process. I mean, that's really exciting. And then the other question is, of course, below the inverse beta decay neutrino energy, like below 1.8, that's a region that, for example, Prospect can't do, but
Yeah.
we can do. The other thing is the breeder neutrinos. That's very low energy neutrinos. That remind me again that you say that's. I always thought that that's like an order of magnitude higher than the,
Yes.
higher energy neutrino.
Yes.
But it looks like for Florida, it's only a 10% for low energy.
Okay, so that one, let me just go back. So the problem is, unfortunately, here we come to fundamental limitation. Where was that? Sorry. That's a very correct observation. The problem is that this reaction and this spin also gets a contribution of neutrinos at 3 MeV, 4 MeV, 5 MeV, and so on and so forth. Right? And so the problem really is that you're not resolving the energy event by event. If you could do this, then you actually would see that the flux from breeding neutrinos is much higher than everything else in low energies, but integrating over the whole spectrum. And integrated over the whole spectrum, the fact that you have 5 times higher flux or so in half an MeV compared to the other 10 MeV is not such a huge effect. And here you're looking at the presence of the blanket, which is a factor 2 variation in the number of breeding neutrinos you have. So it's not a huge effect. So that's why this is hard. And that's actually also one of the real problems, I think, using sevens for reactor safeguards, like studying the general evolution of the spectrum. Since you don't have an event by event resolution, you need many more events that have the same statistical power to do this.
Can you remind me, like, this hardening of the spectrum, or changing it over time, does that have anything to do with the 5 MeV bump or no?
Okay, so how does this, I think, let me make this a more challenging question because I think I can answer that one better. So we have all these anomalies, so what about the 5 MeV bump? So there are several scenarios, right? And so the 5 MeV bump can be the same in all isotopes, right? Then it doesn't matter for anything if said, same analysis. Okay, that's easy. Let's assume the bump is only in plutonium or only in uranium. Then everything here becomes a lot easier because I just need to measure the height of the bump and know how much plutonium uranium I have, right? Or the bump is only in uranium-238, which doesn't matter either because uranium-238 doesn't change during reactor core evolution. So either it doesn't matter, it makes things actually easier. And so that's, for instance, getting a good measurement from prospect to know whether the bump, what's the size of the bump in 235 would be very important. That's, for instance, what when my last slide had, we need more calibration. It's an example.
In diabase, did it not? Diabase trying to do something.
Diabase barely can see the reactor burn up to start with. And the reason is diabase seeing 6 reactor cores. And they're not refueled at the same time to make sure that the lights in Hong Kong stay on. So right, they basically, the diabase are refueling about every 3 months. And so the swing around the average burn-up is very, very small. And so we had diabase barely 3 or 4 sigma sees the reactor, 4 sigma sees the fact that the flux changes as a function of the burn-up. But that's integrated with the whole spectrum. So diabase is not the experimental address just for the 5 MeV. However, Reno, their near detector sees fewer cores, right? The way this is laid out, right? Reno has its reactors lined up like this, and their near detector sits here. So this near detector really mostly sees 1 reactor core, or maybe 3. So they have claimed they see an effect in the bump, which is consistent with this being in 235. Prospect is saying this is not consistent with their data. I think we need just to wait for Prospect to have more statistics to really get an answer. Yes.
So coming back to Ruba's question about the neutrinos, if you have different target, can the ratio change?
Yes. I mean, you want to go journey to the lightest isotope you can find. Right?
Oh, you want to go to lightest
Yes.
isotope in order to have.
And so we picked silicon for this plot for a reason. And xenon, this doesn't look so pretty.
Yeah, well, that's because the threshold, but if you have like single electron division, then you put it better.
Exactly.
Yes.
So,
If you have very low threshold, this becomes.
Right. The ratio looks the same. The question is what's the scale down?
Exactly.
All right, because this is a 1 over E basically. So that's good.
I mean, we are very, I mean, as you know, Connie, they want to strive, I mean, they have small CCDs, but they can reach single electron sensitivity. So if they can put together 100 kilograms, that sort of becomes a perfect mobile platform.
Yeah, I mean, this is actually this paper, which is from 2016. We basically used Coney as our experimental examples. It looks they're close enough to be there and all that. Because they, at the time, were sort of the ones with the most published material.
The only problem is the Lindhard is so bad at that energy. It basically goes to zero.
Yes, no, that's the other thing, of course, you need to understand your Lincoln effect very closely, because if you mismodel that, these two curves become identical. And that's another problem for these applications, by the way. You need to understand your really how these sensitivity rolls off. And that's, for instance, what I meant when I said, there's one thing saying, okay, we've seen it, and then making this a precision tool to study reactor states. There's a lot of work between here and there. But seeing it, of course, is the first important step, otherwise.
Any other questions?
So aluminum might be better for this. If you can't think of a detector based on
Like superconducting aluminum.
no, I'm speaking about sapphire.
Oh, yeah, sure.
Aluminum oxide, yeah.
Right on.
Very light.
The trick is, can you reach a real recoil energy threshold, right? Below 50.
No, with cryogenic detectors, low temperature detectors, we can reach.
Yeah.
So sapphire,
We
I'm
haven't
speaking about sapphire
calibrated,
because
we
they're one
can.
of the best.
Yeah.
So below 50?
Yeah, but we don't have calibration, so we're, like minor, we stop at 100 dB. But there's not,
No, but I'm
we
saying
can.
for future, you can think of,
Future.
very sensitive phonon detectors.
So how low can you go down to?
Sorry?
How low can you go down to?
I mean, there you are not limited by lintard, because, you are measuring directly the phonon, so you can go down.
I mean, that's basically what Crest is trying.
That's what Crest is
Yeah.
doing.
Like 10 years from now, you would probably make this plot differently because you would have already reached below 10 eV.
Yeah, right, you, exactly. I mean, this is, yeah.
All right, well, Patrick, it was Dr. Moore here today.